From section 6.1, the question was, given a graph of a function, what would be the graph of the inverse of the function? So what you do is for every point in the original graph, you should swap the x and the y value. This is the same as considering the line y equals x and taking the reflection of the original graph with respect to that line. So the part that was over here should now be somewhere here, and this part should be something like this. So this would be my sketch of the inverse function, and this should be your choice. From section 6.2, the question was about the best method to evaluate this integral. And the answer should be u substitution. You can do u is equal to negative x squared. The question from section 6.3 is a list of statements. Some of them are true and some of them are false. I will go through the true ones right now. So one of the true statements that might show up is this one. So if the natural log of a number is equal to a second number, then the first number is equal to e to the second number. Another statement is that the natural log of e to a number is equal to the number itself. As x approaches 0 from the right, the natural log gets large and negative. So we put negative infinity symbol here. And as x gets large, the natural log also gets large. And you can make the natural log as big as you want. The question from section 6.6 is what triangle to draw when you try to do implicit differentiation to differentiate y equals an inverse trig function. So I have y equals arc sine of x. I take sine of both sides. So this means sine of an angle y is equal to x over 1. So angle is y, and then x is the opposite side, and 1 is the hypotenuse. So I should have 1 here and x here. And the angle should be y. And this wasn't part of the question, but if you want to actually do the implicit differentiation, you'll also need to compute this third side, which is the square root of 1 minus x squared. From section 6.4, you're asked to differentiate by first taking the natural log and then do implicit differentiation. So first I apply natural log to both sides. So I have natural log of y is the natural log of the right-hand side. And this is the same as x times the natural log of 1 plus square root of x. And then I will perform implicit differentiation. So I wrote down natural log of y and x times natural log of 1 plus square root of x. And I compute d dx. On the left, I have 1 over y times dy dx. And then on the right, I do product rule. So I have x times the derivative of the second part. So that is 1 over 1 plus square root of x times the derivative of 1 plus square root of x, which is 1/2 1 over square root of x. Plus, I take the derivative of x and then just write down the second part. On the next line, I will just simplify a little bit. So I have square root of x over 2, and then 1 over 1 plus square root of x plus the natural log of 1 plus square root of x. And now I'll move 1 over y to the other side. And then I will replace y with one plus square root of x to dx. And this is my final answer. From section 6.8, I have the limit of a function, and part A is to check whether it is an indeterminate form, and if it is, what type. So first I check the limit for 1 plus 3 over 2x. So this limit is 1. And then I check the value for the exponent. This goes to infinity. So this is an indeterminate form. And the type is 1 infinity. So in particular, it is one of these indeterminate powers. And whenever you see an indeterminate power, this method will always work where you set y to be equal to the function you're interested in and take the natural log of both sides, and then first compute the limit of the natural log using L'Hopital's rule. So first I write down y equals 1 plus 3 over 2x to the 5x, and then I take the natural log. So I have the natural log of the whole thing. And now I can bring the exponent down. So 5x times the natural log of 1 plus 3 over 2x. Next, I will compute the limit for the natural log of y using L'Hopital's rule. I can either write five times natural log of 1 plus 3 over 2x over 1 over x, or I can write this as 5x over 1 over natural log of 1 plus 3 over 2x. But this one looks easier. So I will take this format. First, let me check that I can actually use L'Hopital's rule, or if I even need to. So I compute the limit as x goes to infinity for the top function. So the inside goes to 1. So I have 0. And then I compute the limit as x goes to infinity for the bottom function. Because x gets large, 1 over that large value would be 0. So this means that we can attempt L'Hopital's rule of type 0, 0. So I write down natural log of y. So I have 5 natural log 1 plus 3 over 2x over 1 over x. And then I will take the derivative of both the top function and the bottom function. So the top function, the derivative is 5 times 1 over 1 plus 3 over 2x. And then I have to multiply with the derivative of 1 plus 3 over 2x, which is 3 over 2 times negative 1 over x squared. And then the derivative of the bottom function, 1 over x, is negative 1 over x squared. And I see that I can cancel out the 1 over x squared. So I have 5 times 3 over 2, 1 over 1 plus 3 over 2x. And now I see that if I take the limit of this value as x goes to infinity, the value 3 over 2x will go to 0 because 2x will get large. So then this part will be 1. So the limit is 5 times 3 over 2. And now I will continue writing the other limits. I did not write the equal signs before because I wasn't sure that the things I was writing were equal. And the part where I use L'Hopital's rule is this equal sign. So now I'm ready to compute the limit of y as x goes to infinity. So I have e to the limit as x goes to infinity of the natural log of y. So I have e to the 15 over 2. The last problem is to evaluate this definite integral. And you were told that you should do integration by parts. I could try having u be x to the 5 and dv be the natural log dx. But then to compute v, I would have to compute the antiderivative of the natural log, and that requires integration by parts. So let's try swapping the u and the dv. So now I have u as natural log and dv as x to the 5. So then du would be 1 over x dx, and v is x to the 6 over 6. So the definite integral would be uv minus the integral v du. And I said that my u is the natural log, and then v is x to the 6 over 6, and then my v is x to the 6 over 6, and my du is 1 over x dx. So I have x to the 5th over 6 dx. To do this integral, I can just apply the power rule. So I have x to the 6 over 6. So I have 36 here. And now I just need to plug in e and 1. So I have natural log of e to the 6 over 6 minus natural log of 1, e to the 1 over 6 minus e to the 6 over 36 minus 1 over 36. Natural log of e is 1, and natural log of 1 is 0. So this whole thing is 0. So I have e to the 6 over 6 minus e to the 6 over 36 plus 1 over 36. So I have 5 e to the 6 over 36 plus 1 over 36. But it's fine if you stop here.